Okay, the one new piece that we're adding for today is on this page of notes that I gave you before you left class yesterday. And it's about relative velocity. And it goes back to when we talked about relative motion, right? Like that velocity can only be described with respect to something else, right? Like, so when you're in a car sitting beside someone else in the car and you're moving down the street, you're not moving with respect to the other people in the car, but you are to the respect to the people on the street. Okay, so we have to describe velocity with respect to a frame of reference, okay, that has already been defined. Lots of times the frame of reference is when we're like standing, right? So we measure our speed with respect to the houses and the road signs, okay? Sometimes though, when we're moving, there's other things that influence our movement. Like if you're swimming and there's a current, so not only are you moving some velocity, but the water's moving too. If you happen to be moving in the same direction as the water's moving, that's a bonus for you because it'll speed you up. If you happen to be moving into the water, that's not a bonus because you'll be going slower. And then it could be that you're going across. So if you look at this sheet of notes, it says plotting a plane trip using the ground as a frame of reference, but the plane's traveling in the air, which could also be moving. So then you have to look at what's the overall effect. So what I mean by that, I'll cap my pen here, is right, so here you are on the ground and you want to move this way. Okay, so this is what you're doing. So this is your velocity with respect to like the air. But then maybe the wind is blowing really strong, and so maybe the wind is blowing this way. So this would be the velocity of the wind with respect to the ground. So in the end, your resultant then will be the combination of the two of them. You might have wanted to go in a straight line path, but the wind blows you off that path. And so someone standing on the shore or standing on the ground watching sees you going at an angle. For example, let's think about you going across, swimming across the St. John River. You want to swim across to the lighthouse because they're selling ice cream. So you stand on the north side, you swim directly, you aim for the lighthouse here. But the current is flowing this way. And so where do you end up? You do not end up at the lighthouse. You end up somewhere further downstream. And that's what example number 1 on your sheet is talking about. Now I gave you space on the back side to do it back there, okay? I'm just going to do it here so I don't have to flip it over. So it says a person in a canoe is crossing a river to a campsite on the opposite side, okay? So here's the river. The person is traveling, so this is what you're doing. The velocity of the person with respect to the river is 4 meters per second east. But the river is going south. So the river is doing this. So the velocity of the river with respect to the ground or the shore is, north to south, is 2 meters per second south. So what are you going to end up doing? Even though you're aiming straight across, you're going to end up doing this, okay? And it tells us that the river is 800 meters wide, and we'll use that eventually, but we don't need it right now. So the first part of the question wants to know, what is the velocity of the canoe with respect to the river? It's asking for this velocity, your VAV. Well, you can find it. This is a right-angled triangle, so you can just use Pythagorean theorem. So VAV squared is going to equal 4 meters per second squared plus 2 meters per second squared. 16 plus 4 is 20. Take the square root of 20 and you should get 4.45 meters per second. It asks for velocity though, so we need the angle as well. And I'd use tan theta because we know both of these sides. So tan theta will equal opposite over 2 over 4. opposite over adjacent. And when you do that, you get a theta of 26.56 degrees. So the final answer then would be 4.45 meters per second east, 26.56 degrees. Which way did you end up being pulled? South. So this is your final velocity with respect to the shore, even though you were trying to aim straight across. How long does it take to reach the other bank? Well, the river is 800 meters wide, and the velocity that you're going, you have to, so this is your displacement vector here. You have to use your velocity vector that's going in the same direction. So we know VAV is equal to delta D over delta T. We want to know how long, so delta T is equal to rearranging delta D over VAV. So the 800 meters is going straight across the river. That means you have to use the velocity that's going straight across the river, 4 meters per second. And you will find out that the time it'll take you is 200 seconds. Now I'm sure you're all saying, but wait, why don't you use the 4.45? Because if you use the 4.45, it's a different length. You're going 4.45 along this length, you'd have to find the length of this side to use that. So you have to make sure that the delta D you're using is in the same direction as the velocity vector you're using. Part C says, where will the canoe land? So it wants to know, what's this delta D? Well, we have the speed on this side. We know that if it takes you 200 seconds to cross, then it takes the river has 200 seconds to carry you down. So the time has to be the same. So where will you land? You're looking for delta D, VAV times delta T. So you need to use the V now that's going downstream. So it'll be 2 meters per second times 200 seconds. I can hear you all say, what? And so you get 400 meters. It was going south, so this is south. Okay, so let me try this again. So what I'm saying is, you have a river, you want to go straight across. Okay, so this is your speed, 4 meters per second. You know the river is 800 meters wide. It doesn't matter that the current is carrying you down at a rate of 2 meters per second. The length of time that it's going to take you to go straight across, to cross the river that's 800 meters wide, is just dependent upon the component of your velocity that's going across. So even though your velocity ends up being bigger and at an angle, if we're looking at the distance across, you have to use the component of your velocity vector that's going across. Okay, once you have that, you can find the time. And the time that it takes you to cross the river is exactly the same time as it takes the river has to carry you downstream. So once you get that 200 meters per second, 200 seconds, you can then use it with this 2 meters per second to figure out how far downstream have you gone. Okay, so the time for the three vectors is the same, but the velocity and the speeds, the velocities and the displacements of them are not, right? The time it takes you to cross is the same amount of time as the river has to carry you down. So whenever you're doing any with the VAV equals delta D over delta T, you need to make sure you're using the components of the displacement and the velocity that match each other. So you could have found the delta D of this line and then used your 4.45 meters per second and the length of your displacement vector. Okay, now let's just complicate it a little. Let's suppose you don't want to end 400 meters downstream. So now you're like, I'm going to use physics. So if I want to go straight across and the river's going to carry me downstream, well then I want to aim upstream and let the river carry me here so that this now becomes my resultant. And this would be important if you were on a canoeing trip in the Amazon and this is the landing site, right? So you don't want to end up 400 meters downstream